Okay, good morning. So in the previous lecture, we have discussed about the air washer, and after that we started our discussion on the straight line law. So we couldn't complete this. Let me start the discussion again for straight line law. Okay. So as I told you earlier as well, typically whenever we do different processes, for example heating and humidification, cooling and dehumidification, cooling and humidification, etc., what we need to do, basically we need to pass over the air over certain cooling coil or heating coil so that we can achieve the desired process. Okay, so in the process, whenever the air is flowing over the cooling coil or heating coil, then what happens actually, that let us try to understand. Okay, so as far as our initial understanding about the moisture is concerned, we know that if we have certain amount of air, say at thermodynamic state 1, okay, and at state 1, if I am passing the air over the cooling coil, what will happen? Initially, whenever it will be coming in contact with the cooling coil, it will start giving its heat to the cooling coil. So initially what should typically happen, that it should initially lose heat in the form of sensible heat. Okay, and when we will be finding that sufficient amount of cooling has taken place, after that what will be happening? It has rejected sufficient amount of heat, its temperature will keep on decreasing, and finally it will reach to the saturated state 2. After saturated state 2, when we will be doing the further cooling of the air in the cooling coil. Okay, because in cooling coil it is not the process that it is not the case that just you have given a single pass. So cooling coil is having certain thickness. So in that thickness zone, for example, if this portion represents the thickness of the cooling coil, so when air will be entering from this point, then initially it will start cooling. Once it is starting cooling, it may so happen that up to say this point it has reached to state 2. But after this point also, if the temperature of cooling coil is low, then after this point also it will keep on losing the heat. Is this one clear? And whenever after this point it will lose the heat, because it has reached at the saturated state. So after the saturated state, when its temperature will be decreasing, some of its moisture content will also be decreasing, because it is not having capacity to hold the high moisture. So that's why the actual process should happen that 1 to 2 I will be having first cooling, only sensible cooling, and after point 2, once it reached the saturated state, then I will be having combined cooling and dehumidification process. Is this point clear? Anyone is having any doubt about this? Okay. But in reality, when I will be looking into the practical cooling coil, I will not be able to achieve exactly this type of process. Okay, there are certain reasons for that. The very first reason is, whenever we have to achieve this type of process, we are making one assumption that the entire portion of the cooling coil is maintained at single temperature, which is its, say, T3 temperature of the cooling coil. Okay, but in practical cases what happens, different portions of the cooling coil are having different temperature values. Is this point clear? It is not the case that perfectly you will be able to achieve the single value of temperature at each and every portion of the cooling coil. Moreover, over the cooling coil, many times, because over the cooling coil what we are passing? We are passing air. Air typically has less convective heat transfer coefficient. Okay, so in order to improve the, so if you are transferring heat with low convective heat transfer coefficient, you need large area of cooling coil. Okay, so to compensate this, typically what is done, the heat, to compensate the low heat transfer of air, what we do, you have studied in heat transfer. So whenever we have some heat transfer surface and a fluid whose heat transfer coefficient is less, when it is exchanging the heat by convection with the heat transfer surface, then what we do? In heat transfer, have you studied heat transfer? What we do then? What is done to increase the heat transfer from a surface? We use fins, okay, in order to compensate for the low heat transfer coefficient. But typically we try to increase the surface area for the heat transfer. So in the process for increasing the surface area, we put certain extended surfaces on the actual heat transfer surface, which we call as fins. So typically over the cooling coil also we put certain type of fins. So all this stuff, black colored structure is nothing but representing fins. Okay. So fins, in order to have good performance from the fin, what should have happen? What should happen? Fins should have no temperature gradient, so that whatever the temperature at the cooling coil, same temperature is felt at the surface of the fin also. Then only heat transfer will be more effective. But in reality, fin surface is also having certain amount of finite thermal conductivity. So because of the finite thermal conductivity, there will be certain temperature gradient on the fin surface as well. So all these things will not be leading to the same value of temperature at cooling coil as well as the fins, which are participating in the heat transfer process with the air. Is this point clear? Second important point is whenever you are passing air over a cooling coil, okay, because of the boundary layer phenomena, what happens? Only certain portion of the air comes in direct contact with the cooling coil, whereas significant amount of air will be escaping through the gaps in between the cooling coil and the fin surfaces. Is this point clear? For example, I have tried to show you this picture. So if this is my duct, and in this duct this is my fin and cooling coil arrangement. Okay. So now if I enlarge this individual box, so if I enlarge the individual box, it will be a large structure. In this large means upon enlargement, it will be looking a big view. So zoomed in view. In this zoomed in view, you will be finding that all across some air is passing through this. Okay. Now you will be finding in this box only the portion which is in immediate contact, that is having the perfect contact with the cooling coil or the fin surface. Okay. Whereas the air which is passing through the center, it is not having any contact. Now moreover, what will happen? There will be formation of a thermal boundary layer. So thermal boundary layer will be forming structure something like this. What it means? Inside this gradient of temperature will exist, where after this point the temperature will be almost free stream temperature, and only in this temperature the influence of the cooling coil will be felt. Is this point clear? All are clear with this point or not? So it means that whenever the air passes over the cooling coil, the entire mass of the air does not come in perfect contact with the cooling coil. Only a fraction of the air comes in perfect contact with the cooling coil. Is this one clear? So significant amount of bypass takes place. Next important point is, if my cooling coil is at temperature T3, what will happen? The air which is in immediate contact with the cooling coil, it should immediately try to reach the temperature of the coil. Okay. So the air which is in perfect contact or in the immediate vicinity of the cooling coil, its temperature will try to become equal to that of the cooling coil temperature. So what will happen? In that particular fraction of the cooling coil, immediately the dehumidification will take place. Okay, so and it will not wait for the remaining portion of the air first to come to this saturated state and then decrease its temperature. That particular portion will be having immediately the what? Dehumidification. Okay. So because of all these reasons, whatever the actual process we think that should take place, instead of this, what I can do, I can join point 1, which is the incoming state of the air, with 0.3, which is the temperature of the cooling coil, and I can join these two by a straight line. Okay, and now depending upon how much amount of bypass is taking place, my exit state of the air out of the cooling coil will be somewhere over here. Say this is my state A is exit state of the air from the cooling coil. Okay, so the process which appears to follow path 1 to 2 to 3 on a the process which appears to follow path 1 to 2 to 3 on a cooling coil which will have perfect contact with the air and whose temperature will be always maintained at the same temperature value. That process, instead of following this path, typically follows this straight line, and on this straight line the state A will be controlled by the amount of bypass mass flow rate of the air. For example, if lesser is the bypass air, it means that more amount of air will come close to that of the temperature of the cooling coil. So my state will be somewhere close to 0.3. If more is the bypass, I will be more closer to the inlet state 1, say A double dash. Is this point clear? All are clear with this point? So this type of law is something which is called as straight line law. So due to all the constraints which I have specified over here, because of these constraints, instead of following the actual theoretical process, my practical process will follow a straight line in between the apparatus temperature and the incoming temperature, and depending upon the amount of bypass, I will be having some exit state. Is this one clear? More is the bypass, exit state will be close to the inlet state of the air. Lesser is the bypass, exit state will be more closer to the apparatus temperature. Anyone is having any doubt about this? Is this one clear? Now let us, if I have to define efficiency of this heat transfer process. So my inlet state was T1 at T1 temperature, exit state is A, so minus TA, that is the actual cooling which has taken place. Okay, what would have been the maximum amount of cooling if entire air would have physical contact? So T1 minus T3. Is this point clear? All are clear with this point or not? So typically the temperature of the cooling coil, which is generally marked on the saturated curve. Why it is marked on the saturated curve? Because this is the maximum amount of cooling which cooling coil will be able to. Okay, so the temperature of the cooling coil, of course it will not be always the same temperature at different portions of the cooling coil. Okay, but practically assumed average temperature of the entire cooling coil surface is typically known as apparatus dew point temperature. So this is known as ADP. Okay, is this one clear? What is apparatus dew point temperature? The average temperature or average effective temperature of the entire cooling coil surface is something which is called as apparatus dew point temperature. So the efficiency of the cooling process I can simply write as T1 minus T actual exit state divided by T1 minus T ADP, where ADP is the apparatus dew point temperature. All are clear with this point? Now let's talk about bypass factor. So I told you that certain amount of air is actually not coming in contact with the cooling coil and it is just leaving the cooling coil without having actual physical contact with the cooling coil. So the amount of air which is not coming in contact with the cooling coil, that is quantified in terms of the bypass factor. Okay, so how to study or how to specify bypass factor, that let's understand. Let's consider that m dot A is the mass flow rate of the air which is flowing over the cooling coil, entire mass flow rate. And let me assume that x is my bypass factor. Okay, and x into m dot A is the mass of air bypassed. It means it has not come in contact with the cooling coil. So what will be mass of air which will be passing through the cooling coil? 1 minus x into m dot A. Okay, 1 minus x into m dot A is the mass of air passing over the cooling coil. Now let's understand that this is state 1, which is inlet state to the cooling coil, and this is my ADP. Is this one clear? So now if this is ADP, this is inlet state, then I will be finding that my exit state will lie on this state. However, at which point it will lie on, it will depend upon the value of bypass factor. Let me assume that my exit state is state 2. Is this one clear? So state 1 is, the situation is like this. This is the cooling coil. Air is flowing over cooling coil. So what I said, that m dot A is the mass of air coming. Now over the cooling coil, whatever mass is coming, that is 1 minus x into m dot A. And the mass which is not passing over the cooling coil, that is x into m dot A. Is this one clear? And finally again this entire is mixing and this air is becoming m dot A. All are clear with this idea? Now if you assume that state over here was 1 and the cooling coil temperature is ADP and the state at the exit is 2, then I can say that whatever the air which is coming in direct contact with cooling coil, its temperature will obviously be equal to that of the temperature of the cooling coil. So it means that 1 minus x into m dot A amount of air, and if I multiply with Cp of moist air, it will be having energy content equal to that of this TADP, because it is coming in perfect contact with the cooling coil, so it must reach the temperature of the cooling coil, plus x amount of m dot A air has not participated in the cooling process because it has not come in contact with the cooling coil. So if it was entering with enthalpy 1, it will also leave with enthalpy 1. Enthalpy 1. Finally, when this air and this air mixed together in the duct, these have resulted in the m dot A amount of air and its enthalpy is H2. Is this one clear? Again, this H1 I can write as, what I can write H1? H1 I can write as Cp Ma into T1, and H2 I can write Cp of moist air into T2. Now m dot A into Cp is common in the entire equation. It will be cancelling out. I can simply write that x times of T1 minus T ADP equal to T2 minus T ADP, correct? Is it correct from this equation? So finally my x has become nothing but T2 minus TADP upon T1 minus TADP. So I can represent that T2 minus TADP is this portion. So this represents X friction and this represents 1 minus X friction. All are clear with this point or not? Okay. Now, because what is this? This is a straight line and these are just the ratio of horizontal projections of this line. The way this ratio of horizontal projections are satisfying, in the similar way vertical projections should also satisfy because it's a straight line. Okay. So from this geometric similarity I can write that it can also be written as W2 minus W corresponding to ADP upon W1 minus W corresponding to ADP. Is this point clear? Anyone is having any doubt about this? All are clear with this point? So once we have understanding of the bypass factor and the straight line law, now we can move towards the design of air conditioning systems. Okay? All are clear with this point or not? So let's now study about the air conditioning system. So typically in an air conditioning system we have two types of loads. One is called as sensible heat load and other is called as what? Latent heat load. Okay. For example, this is the room. In this room how many tube lights are there? Okay. And all these tubes have what? Certain wattage capacity. For example, some tube will be of 20 watts capacity, some can be of 100 watts capacity. So what is the meaning of these? It means that at this rate these are releasing heat to the room here. Okay. Then other than that, if I operate the fan, then fan will also impart certain amount of energy. Okay. Then you have so many windows. Okay. Through these windows solar radiations are coming inside. These are also adding certain amount of heat. You all are sitting over here, so our body is also, because of the metabolism, releasing certain amount of heat. Okay. So when this entire heat will be accumulated together, then we will be calling this as sensible heat. Other than that, when we are doing actually respiration, so we are injecting certain amount of moisture. Okay. If I have kept some glass of water open over here, from there also evaporation will take place and that will add certain amount of moisture. Okay. Then my door is open, so from outside ambient also some amount of air is coming and it's a moist air, so that will also add certain amount of moisture. So it means all these things which will lead to increase in moisture content of the room, that will be coming as a latent heat load, and the sum of these two will be my total heat load. So typically in a summer air conditioning system, all these loads will be positive. What is the meaning of this? If this is the room, then basically this sensible heat is added to the room. So it's RSH. Similarly, this latent heat is also added to the room. So ultimately, whatever this is a heating load on the room, the cooling coil is designed in order to cool this load from the room. Then only we will be able to maintain the room at the desired temperature. Okay. Is this point clear or not? For example, if room is initially at 22 degrees Celsius and 50% relative humidity, and then at certain rate my sensible heat and moisture is coming into the room, I have to remove at that rate only the sensible heat and moisture from the room, then only I will be able to maintain the room condition. If there is imbalance in between the incoming and the amount of heat which we are removing in the cooling coil, then my room temperature will either increase or decrease. Okay, when it will increase? When my cooling coil capacity is less. If cooling coil capacity is more, then it will be further decrease. So in order to maintain the condition, whatever load is coming, that load I have to actually remove. Is this one clear? So that is the actually task of the air conditioning system. Now we have different type of air conditioning system. First, let us try to understand the simple air conditioning system. And moreover, remember one point, whenever I am trying to describe these air conditioning system, at present I am considering that the design of air conditioning system we are doing for the summer air conditioning systems. Okay, whenever we will be going for winter, in winter what will happen? Yes, so the transfer of this heat will be in the reverse direction. Okay, so heat will be losing from the room, and in order to maintain the room at the same condition, I must add the heat on the room. Okay, so it means that in summers, the load is the cooling load on the room and on the cooling coil, and whenever we are operating in the summers, then we have to supply the heating load. Is this one clear? Now let us first understand the simple air conditioning system. So simple air conditioning system is simplest of the all. What is the layout of this system, that let us try to understand. Say this is my room. In this room I am having certain heat leakages, and these heat leakages are reflected in terms of the room sensible heat and room latent heat. Is this one clear? And sum of these two I can call as room total heat load. All are clear to this point? And let us consider that this room is maintained at temperature Ti and humidity Wi. So typically the subscript I over here refers to the indoor conditions. Is this one clear? And let's consider outside ambient temperature is T naught and humidity is W naught. So O over here refers to the outdoor conditions. Is this one clear? So what is our requirement? Our requirement is to maintain the indoor conditions. Now on this room, there is sensible and latent heat load. Okay, so if I do not do any processing of the room air, then ultimately what will be happening? Because of this load, the temperature and humidity of the room will start increasing. In order to maintain this, what I will do, I will take certain amount of air from the room, m dot as, and I will pass this air over a cooling coil. This is my cooling coil. And of course, to circulate this air, what I must have? I must have a fan, because fan will be circulating. So m dot as, I have taken again the same amount of m dot as I have passed over the cooling coil, and then what cooling coil will be doing? Cooling coil will be decreasing its temperature and humidity. Say cooling coil and fan has decreased its temperature and humidity to conditions Ts and Ws, where S refers to supply conditions. Whatever the processed air or conditioned air we are supplying to the room, it is having temperature Ts and humidity Ws. All are clear with this point? And here what I will be having, this room is coming from the air, so at the inlet of the cooling coil, it will be having temperature Ti and humidity W. All are clear with this point? Now, if I have to write room sensible heat, how much it is? M dot. So what I am assuming now, I am assuming that whatever the room sensible heat was added on the room, same amount of heat was removed in the cooling coil. Okay, same amount of heat was removed in the cooling coil. Similarly, whatever RLH was added, same was removed in the cooling coil. Because if the same amount of heat is removed in the cooling coil, then only my conditions will be maintained to Ti and W. Is this point clear? So that's why I can write that RSH, room sensible heat, must be equal to mass flow rate of supply air into Cp of the moist air into, in cooling coil inlet temperature was Ti, outlet temperature is Ts. Okay, so how much heat is removed? M dot As Cpma into Ti minus Ts. Okay, this is the heat removed which is sensible heat. All are clear with this point? Likewise, how much latent heat is removed? M dot As into how much amount of moisture is removed? M dot As into Wi minus Ws. This much moisture is removed. So whenever moisture goes out of the system, it also goes with latent heat of vaporization, whose value can be approximated for engineering calculations 2500. Okay, HFG. So 2500 into M dot As Wi minus Ws. This is the latent heat. What will be RTH? If I am not doing the summation, simply I am writing the RTH in equation form. It will be simply equal to M dot As into total enthalpy change. So total enthalpy change would be Hi minus Hs. All are clear with this point or not? Now let's assume that if at standard condition QVS is the corresponding volumetric flow rate at STP, whatever we are recirculating. So Q dot Vs is what? Volumetric flow rate of air. And where? At STP. If this is volumetric flow rate at STP, then we already have derived the simplified formulas. For sensible heat it was how much? 0.0204 QVS into Ti minus Ts. Okay. For latent heat, how much was it? 50 times QVS into Wi minus Ws. And for total heat, how much was this? 0.02 into, tell me, QVS into please tell me. Have you not written in your notes? 0.02 QVS into it means you are not practicing numerical problems. Are you able to find or not? Shall I show over here where I have done this calculation? Please tell me. You are not able to find it? Let me show you over here. Have I added or not?
Yes, sir.
Added? What is the value?
50.
Okay, final formula I might not have given, but it will be coming out to be 0.02 QVS into whenever I will be substituting in terms of temperatures, then simply okay, Hi minus Hs. Is this point clear or not? Okay, now these loads are clear to you or not? This must be the load. Now, how to represent this on cooling coil? Or in other words, it will also be important to know that what should be the temperature of cooling coil which will be able to achieve this much load. We need to define the temperature of the cooling coil also. So how we can do this? I can define RSHF. What is the meaning of RSHF? Room sensible heat factor. Room sensible heat factor will be equal to RSH divided by RSH plus RLH. This will be my room sensible heat factor. Okay. If I know, now let's think from the design point. If I know the indoor condition, what is indoor condition? If I know indoor state and if I know the RSHF, okay, room sensible heat factor, then what will happen? From alignment circle, I can draw a line on RSHF scale and that will be giving me a line, and if parallel to RSHF line I draw a line over here, that will be my line representing the process on the cooling coil. All are clear with this idea or not? Okay, and where this line will be intersecting the saturated curve, that will be my nothing but the ADP, apparatus dew point temperature. All are clear with this point? Now, my supply state must lie on this line depending upon the bypass factor and the mass flow rate of the air. So, S state will be somewhere on this particular line. Is this point clear? All are clear with this idea? So, if I know RSHF, from RSHF I can, with the help of alignment circle, I can draw a line with parallel line which is passing through state I. When that line will be intersecting the saturation curve, that will be my temperature of the apparatus dew point. Okay, and now depending upon how much flow rate of the air we are circulating and what is the bypass factor, I will be having some supply state of the air on this line. Is this point clear? This I have explained in the graphical way. Let me also explain the same concept with the help of, let me also explain you the same concept with the help of equations. So basically, how many number of equations we have over here? Please tell me. This is equation number 1, which is for room sensible heat. This is equation number 2, which is for room latent heat. I have 2 equations, and how many unknowns I am having? First point is I do not know about what should be my supply state. So Ts and Ws are my 2 unknowns. Do I have any other unknown? Whenever we are circulating this amount of air, I don't know how much should be the amount of the air which we are recirculating. So I can say that from this equation that QVS is also my other unknown. That will be my third unknown. Okay, all are clear with this point or not? So from the mathematical point of view, I am having only 2 equations, whereas I am having 3 unknowns. So how to determine this? But one important point I have to consider over here. Even if I vary my value of TSWS and QVS. Okay, one will be constraint. Is this point clear? One parameter will always be a constraint parameter. It means the volumetric flow rate of supply air, it will act as a constraint, because if I use this value to some value of say y1 corresponding to this, when I will be substituting QVS over here, I will be getting some value of TS and WS. So corresponding to y1 value of QVS, I will be having some value TS1 and WS1. Is this point clear? Similarly, if I choose some another value y2, corresponding to that, my supply state TS2 and WS2 will be changing. All are clear to this point or not? So it means upon varying the value of QVS, my supply state is actually changing. Number one point is clear. But second important point also, we have to understand that though upon changing the volumetric flow rate, my supply states are changing, but ultimately these supply states are corresponding to equations 1 and equation 2. It means that even if my supply states are different for different volumetric flow rate, but ultimately these are satisfying equation 1 and equation 2, which are corresponding to the given amount of sensible heat load and latent heat load. Okay, so it means that all these supply states must lie on the same sensible heat factor line. Is this point clear? So it means that, it simply means that if my supply state is S1, corresponding to this volumetric flow rate will be QVS1. Okay. If I use some another volumetric flow rate QVS2, then my supply state may be S2, supply state may be S3. Likewise, I can have different supply states if I simply vary the volumetric flow rate. But for each volumetric flow rate, I will be having the unique value of the supply state, which will be satisfying the equations 1 and 2, and that's why all the supply states for corresponding different values of volumetric flow rate of the air must lie on this straight line. Is this point clear or not? Anyone is having any doubt about this? This is one very important statement. Okay. So for all the volumetric flow rates, my supply state will be lying on the same straight line. And for each volumetric flow rate, there will be some unique value of the supply state. And another important point is, what should be the minimum value of the volumetric, because if I decrease the volumetric flow rate, then contact of the gas with the cooling coil will be increasing. So I will be approaching more towards the apparatus dew point. If my amount of air is more, then there will be high chance of bypass. So I will be moving more closer to the point. So it means that volumetric flow rate on this line is increasing in this direction. This is the direction of increasing volumetric flow rate. Okay. Now, what should be the minimum amount of volumetric flow rate that I have to recirculate in order to achieve the corresponding room load conditions? Let me assume that QVS value is decreased to such an extent so that my supply state is converted directly to the apparatus dew point. Okay. So QVS minimum will be nothing but equal to RSH upon 0.0204 into Ti minus TADP. Okay, that will be the minimum amount of volumetric flow rate which I have to supply. All are clear with this point or not? And in other words, I can also write it in terms of latent heat load, RLH upon 50 into Wi minus WADP. And it can also be written as RTH upon 0.02 into HI minus HADP. Okay, so this must be the minimum amount of volumetric flow rate which I must recirculate. If I am not circulating this much amount of minimum flow rate, if I go below this, then I will not be able to meet the corresponding RSH and the RLH values. Okay, and I will not be able to maintain the same indoor conditions. All are clear with this point or not? Okay, but in real practice, I will not be able to achieve corresponding to ADP. So in real practice, I will be having some supply state S which will be with some bypass factor X, and here I will be having 1 minus X. All are clear with this point? Anyone is having any doubt about this? Is this point clear? Because in real case, because of the bypass, I will be having certain amount of temperature and humidity higher than the ADP value. So the actual temperature difference Ti minus Ts is something which is called as dehumidified temperature rise. This is called as dehumidified temperature rise. Okay, and the flow rate corresponding to this condition, is something which is called as dehumidified volumetric air flow rate. All are clear with this point or not? Clear? Now my question is, if I put you inside this type of room, will you be comfortable inside the room for 10 hours? Will you be comfortable inside this type of, with this type of system? Will you be comfortable? Comfortable, or what issues you will be facing?
Completely dehumidified.
No, it is not dehumidified, it is at the comfort condition, 50% RH. Your WI is as per that. Will you be comfortable in this room for 10 hours? If this type of AC is installed?
No fresh air is coming.
Yes, so the issue is odor and CO2 concentration. Okay, so it means this air will not be fresh air. Okay, so it will be having certain foul smell, etc. may come, and of course CO2 concentration will be the another issue. So what we need to do, simple system will not be suffering for long. Okay, so we have to have summer air conditioning system with ventilation. We must have certain ventilation. With ventilation, and initially let's consider, because when ventilation comes, then system becomes a bit complex. So if I jointly explain you ventilation and bypass factor, then the process will be becoming a bit complex. So let me first explain summer air conditioning system with ventilation and zero bypass factor. What is the meaning of this? There is no bypass here. It means my supply state will be equal to that of the apparatus dew point temperature. Okay. So in this type of system, what typically we do? Again, I have a same room where some amount of RSH is coming and some amount of RLH is coming. Okay. And the room is maintained at Ti and Wi as the indoor conditions. Then what I have done, I have taken m dot as amount of air, but I have not recirculated the entire amount. M dot A naught amount I have sent outside, and I have only circulated m dot AR amount, that is the recirculated air amount. And in this recirculated air, what I have done, from the ambient I have added m dot A naught. Whatever the mass of the air I have removed, same amount of mass of air I must add from the outside. Okay. Now these two m dot AR and m dot A naught have merged together. Again they brought my mass flow rate to m dot AS. Then I have a cooling coil. Then I have a fan, and this cooling coil and fan then are supplying, say, let me call this supply state as state 2. The state which is coming after mixing of atmospheric air and recirculation air, let us consider it as state 1. Okay, and of course at this point whatever the state will be coming, this will be state I. Here also it will be state I as the indoor condition. And whatever this m dot A naught is coming, it must come with state O. All are clear with this type of system? So schematically it looks very nice. Certain amount of air you have removed, same amount of air you have taken from the atmosphere, and then you have added. Okay. How it will be actually changing the load scenarios. First important point you have to understand is that this recirculated air is coming at which temperature? I. So, and this A naught is coming at which condition? O, outdoor condition. And in summer, TO will always be greater than TR. So, first point is that whatever the m dot A naught air is coming, because of, and mainly it is coming because of ventilation. So, because of ventilation, whatever the air we are adding, it is leading to more load on the cooling coil in comparison to the one if we would have simply recirculated the entire air. Is this point clear? Second drawback of the system is that whatever the m dot A naught air you are sending outside from the room, this air is going with which state? It is going to the ambient at the room air condition. Okay. So it means that this is certain amount of penalty on the system. If I can utilize this cold air to some extent, cool the outside atmospheric air, and then if I send, then my system will be more effective. Is this point clear? So there are two type of losses. One loss is whatever air we are sending outside from the room, that we are sending at the indoor conditions, which was earlier cooled by the cooling coil. And second penalty is whatever outside ambient air we are taking, that we are taking at T0 temperature, which earlier would have been at temperature Ti. So it means that now my effective load on the air conditioning coil will not be only RSH and RLH. There will be some additional load which will be coming because of the recirculation of the outside air or infiltration of the outside air. Okay. So how it will affect the performance of the system, that we will discuss in the next class.